Chapter 13, we start looking at matrices. The order is another way of saying the dimensions. And when we give the order of a matrix, we're giving it in terms of its rows by its columns. So this matrix is a 3 by 3. When we talk about A sub 2 comma 3, we're asking what is the element in the second row, third column. So the second row, there's the first row, here's the second row. Third column, first, second, third column.
Michaela Lewis, if you're in the building, please come to the student
So
office.
the element in the second row and third column is a 4. To multiply matrices, we do row times column. So we're going to do the first row times the first column here. And in order to multiply, the dimensions need to be the same inside the two matrices. So this first matrix is 3 rows and 1 column. The second one is 1 row, 3 columns. When I say the inside dimensions need to be the same, I'm talking about those two numbers right here. Those ones in this case. The outer dimensions, that 3 and that 3, those will be the size of the new matrix, the size of our product. So when I multiply here, I do first row times first column. 1 times negative 2 is 2. And that's it for that column. Then I do the first row times the second column. 1 times negative 1 is negative 1. And then I do the first row times third column. 1 times 4 is 4. Now I do the second row times each column. 2 times negative 2 is negative 4. 2 times negative 1 is negative 2. And 2 times 4 is 8. Now I do the third row times each column. 3 times negative 2. 3 times negative 1. And 3 times 4. Here's our product. We can do this in the calculator also. What I'm going to do is I'm going to go to my matrix menu, second, and then the key that's fourth down there, and I want to edit these matrices. I want to edit matrix A. A is a 3 by 1. And I'm just going to punch these numbers in. 1, 2, I push enter each time to advance. Now I quit. I go back to my matrix menu. 2, negative 1, 4 is going to be matrix B. It's a 1 by 3. Just double checking quick. Negative 2, negative 1, 4. The downfall to using the calculator for all this is if you mess up one number, it's going to throw off everything that you do with this matrix. So it's a good idea to double check what you're putting in. Now we're just going to type in A times B. So we go to our matrix menu, under names we select A, hit times, go back to our matrix menu, select B. And there is the matrix that we just came up with, doing it by hand. In the second example, we're going to do row times column again, the entire row times the entire column. So we're going to do 5 times 2, which is 10, and then we're going to add negative 1 times negative 3. Then we're going to add 0 times 1. And that's the only column, so we stop. And we're going to move on to the second row times that column. Negative 2 times 2 is negative 4, plus negative 2 times negative 3 is 6. Negative 1 times 1 is negative 1. And now we just add those numbers up. We get a matrix that is 13 in the first row, and we get 1 in the second row. And one thing to remember is we could do this matrix multiplication because this is 2 by 3, this is 3 by 1. Those inside dimensions are the same And notice that our product ended up being a 2 by 1. Inverses. If two matrices are inverses, when we multiply them together, we'll get what's called the identity. And the identity matrix, at least for a 2 by 2, is 1, 0, 0, 1. The identity will always have 1s on the main diagonal, which is that downward diagonal right here. A 3 by 3 identity would be 1, 0, 0, 0, 1, 0, 0, 0, 1. And what the identity is, it's similar to the number 1. We can multiply by 1 and not change the value of something. Similarly, if we multiply a matrix by this identity, it doesn't change the value. So what we're going to do here is we're going to find a matrix, the inverse of this, that when we multiply by this A matrix, we'll get the identity every time. And the way we do that is we take 1 divided by the determinant of A. This absolute value kind of notation stands for determinant of A. And that is equal to A times D minus B times C. It's the downward diagonal minus the upward diagonal. And then in the matrix itself, we're going to swap the main diagonal elements and make the other elements on the other diagonal opposites. And we'll go through how to do this in just a second. But one thing to note is that if the determinant is equal to 0, our matrix is what we call a singular matrix, and the inverse doesn't exist because we would have 1 divided by 0 for that scalar multiplication out in front. So if I can use matrices to solve systems. I can set this system into a matrix equation. The first matrix has the coefficients. The second matrix, x, y, that's the variable matrix. And then this is going to equal the constant matrix, what the things are equal to. And if I did matrix multiplication on the left, I would get 2x plus 1y. And second row, we get 3x plus 4y. Now what we're going to do, we're going to look at this as an equation A times x equals b. Matrix A times matrix x equals b. Now if I want to solve for x, with numbers we just divide, but there's no such thing as division with matrices. So what I need to do is I need to multiply by the inverse. And the only way we can take the inverse times matrix b is if we do it on the left. Because this is a 2 by 1, this is a 2 by 2, and its inverse will be a 2 by 2. So I can't do a 2 by 1 times a 2 by 2. That wouldn't work because of the inside dimension. So it has to be on the left-hand side. Matrix multiplication is not commutative. A times B can definitely be different than B times A. And what we get here is the identity matrix. So matrix X is equal to A inverse times B. So let's go and sit down and find the inverse of matrix A. 1 divided by the determinant, which would be 8 minus 3, times the main diagonal element swapped and the other two made opposite. And then you could either multiply the 1/5 in, or you could leave it like this. And I'm actually going to leave it like this for now. So to find x, we're going to take that inverse, 1/5 times 4, negative 1, negative 3, 2, times 4, negative 1. And I'm going to do my matrix multiplication. 4 times 4 is 16, plus 1 is 17. Negative 3 times 4 minus 2 would be negative 14. So my solution is that x equals 17/5 and y equals negative 14/5 after I do the scalar multiplication by 1/5. For a 2 by 2, this isn't a terribly difficult thing to do by hand. Once you get bigger than a 2 by 2, though, the work becomes considerably more. And so we're going to rely kind of heavily on our graphing calculators as we get bigger. But first, let's look at some matrix operations here. I want to find A inverse in a form that's linear, that is a number times matrix A plus a number times matrix I, the identity, where R and S are scalars, just numbers. So what I can do is I don't want the A or the I to go away. It was suggested in class that maybe I could write I as A times A inverse, but the problem is I want I in my answer. So I don't want to replace that. But I can do A times A instead of A squared. And then I can multiply by A inverse. And what I get here is those A's will cancel out. That is giving me the identity. And on the right-hand side, matrices are distributable. So I'm going to have 2 times the identity plus 3 times A inverse. A inverse times the identity. Remember, multiplying by the identity doesn't change the value. So on the left, I just have A equals 2I plus 3 times A inverse. And I have what I want. I want an A, I want an I, and I want an A inverse. I just have to solve for A inverse. I can subtract matrices, that's legal. One thing to know about matrices is there is no such thing as division with matrices. So we're not going to divide by 3 to get rid of this. We're going to multiply by 1/3. So we get 1/3 A minus 2/3 I is equal to A inverse. So we just found an expression for the inverse of A. So as you're working through this, I really recommend that you read, because it's going to talk a lot in the book about how matrix properties relate to real number properties, and some things are the same, some things aren't. Like commutativity, the order matters with matrix multiplication, whereas it doesn't with numbers. 2 times 3 and 3 times 2 are the same thing. But matrix A times matrix B does not always equal matrix B times matrix A. So read these sections. It will give you a much better understanding of what you can and cannot do with matrices.